Sorry. Sorry. This microphone is live. It's not okay. 10 minutes to go. Yeah. Here we have one student or professor. Okay. And what's your first name? Adriana. Adriana. Yeah. Adriana. That's a pretty name. It's musical. Adriana. My granddaughter is Isabella and Liliana. Liliana. Adriana. Do you have a nickname? A short name? Adrian. Yeah, that's nice too. Yeah, that works. How about we nickname one of our grandchildren Addie? Would you eat green eggs? That's the title of Green Eggs and Ham. Would you eat eggs that are colored?
Okay, so let's start. I would like to welcome you very, very warmly. I know it's still vacation period, and it's really great that you are here. And we have this great opportunity to welcome Charles Weber, who is from Chicago, Loyola University. He used to work at the Cell and Molecular Physiology department. And together with Professor Bilut, Charles is an inventor of a method that is applicable to many, many branches of science. And we are very, very grateful that you found the time to not only give us a lecture today, but also consult some of our projects. Today, Charles will be talking about detecting deterministic language patterns in dynamical systems across disciplines. So you can see that language here is not just language that you hear now, but it's understood much more broadly. And I must say, I was really taken to this method and encouraged to apply it by Guy van Orden, who unfortunately is no longer with us. But Guy van Orden noticed that human behavior is so complex and so multi-level that ordinary linear methods are not enough, and we need to seek for something better. And this method, I think, is something better because it's at the same time, it's extremely intuitive, and then it's very, very deep in acknowledging the complexity of the systems. So Chuck, the floor is yours. I just wanted to mention that Chuck is also a great help in any projects that you have. The minute he sees you, he asks, "Where is your data?" and just wants to analyze it quickly. So please take advantage of that as well. Thank you. And I'm giving the floor to Chuck.
Thank you very much, Dr. Leonardi. I appreciate the invitation to visit Warsaw. The last time I was in Warsaw was in 1974. And it was quite a different country and quite a different city at that time. So it's a joy to come back. We have seen Poland colored. It's gone from gray, brown, and white earthen tones to more color. And this is a wonderful thing. The topic I want to talk about is, yes, recurrence analysis. And the idea of recurrence analysis is that many things in time and space happen once, and then they happen again and again. So you can think of just your walking pattern. You put left foot, left foot again. So in other words, your left foot's always recurring, and your right foot's always recurring. But they come at different time intervals. If you're running, you have a different gait. You have a different type of pattern. And we can put this to both a graph, and then we can quantitatively extract features from what we call recurrence plots. Joe Spillett, my collaborator, is the one who, with his help and our collaboration over many years, have taken recurrence plots, which were really reported back in 1987 by Ekman, Ruel, and others. And what happens is that plots were made, and our question was, these plots are nice, but we see them differently. And to see them quantitatively, we had to extract features from the plot. And so there's many different definitions. We came up with 5, Norbert Marwan came up with another 3, and more. Keep multiplying. You could do this. So as you look at these plots, you may be able to come up with your own measures that will explain the data that you're looking at. I'm trying to make this talk kind of general in a sense. Let me give you the conclusion today first. If you get this, that's what the whole talk is about. And what I'm saying is that when you look at the world in which we are living in, there's patterns all over the place. And for an untrained eye, you can walk past things and you don't recognize what you see. So for example, if you commute back and forth to work, can you reproduce all the stores that you pass? You've done it for 20 years. Can you do it? And so there's things that our mind just blocks out. And we go through life like that. There's something about seeing and deeply seeing. I saw artists on the street today drawing pictures of the cathedral. And so they're trained and they're learning how to do this. Or actually, we can say they're learning how to see. What I want to say, my conclusion today is that all of nature is speaking, the language, okay? That's my conclusion. And so when you see that, you can say, okay, what are these chairs saying? What is a rock saying? What are stars saying? What are movements of the human body saying? And I'm going to show you how to use one specific example of the human heart, and we're going to convert the human heart into a text, and then we're going to pronounce it. And you can actually hear it. And we're going to show you how this works. And then when you start looking at things, you can say, I wonder what that sounds like. What is it saying? In other words, it's a language. And the way we prove it's a language is by we scramble the letters in the language, and then it comes up as nonsense. Now, you're not going to be able to read the text of what the heart is speaking, but believe me, it's speaking. So because I'm a generalist, I don't like cutting things apart. I like gluing things together. So an integrationist, so I'm very comfortable in many different fields. And I'm thrilled that recurrence analysis has been used to express the analysis in many different fields. So we're talking astronomy, we're talking mathematics, physics, psychology, sciences, and so forth, and like you are. And it's way beyond what Joe Spillett and I ever dreamed of back in the early 90s. And I know Scott Kelso, who is your advisor, Dr. Leonardi, and I know several people in the psychology field, which, and I'm not a psychologist, I'm trained physiologist. So that means I study the life sciences. And I used to joke, what's your definition of physiology? I would ask my nursing students. And I said, what's your definition of physiology? He said, well, it's comparing heart and lungs. I said, no. Physiology to me, if it's wiggling in time and space, that's physiology. As soon as it freezes and stops, now we're talking anatomy. Okay, now it's anatomy. So you've heard of steady state. Steady state, we say, where things are kind of regular and unchanging. Steady state to me is the cadaver state. That's a cadaver state. So it's not moving. It's not living. It doesn't have a dynamic to it. So it's very static. It's like a still photograph. So that's what I'm going to show you today is how you can view, no matter what you study, view it as a language and view it as speaking. And you can say, well, what if my system has a stroke? Its speech changes. And you can detect that in your system. And you can say, when did that happen? Well, you look at the data. Show me the data. So let's do this. Here's a language in English. Now, the first word, FI. There's no such word except for fee, fi, fo, fum in children's music, things like that. But I'll read this for you. Not everyone can read this. If you can read this, you have a strange mind too. I couldn't believe that I could actually understand what I was reading. The phenomenal power of the human mind, according to a research at Cambridge University, it doesn't matter in what order the letters a word are in. The only important thing is that the first and last letter be in the right place. The rest can be a total mess, and you can still read it without a problem. This is because the human mind does not need every letter by itself, but the word as a whole. Amazing, huh? Yeah, I always thought spelling was important. If you can read this, share it. So that's, I don't speak or read Polish. I wonder if this would work in Polish. The first and the last letter are most important. As you scan, you read so fast, and you see a whole, you don't need those middle letters. Are you familiar with the literature of Edgar Allan Poe, famous American artist? I want to talk about the telltale heart. And the reason I want to talk about the telltale heart, because it speaks of the heart of a man who was murdered still speaking. And I'm going to show you how to make a heart speak, okay? And this could be done to each one of you if we just record you. This would not be a problem. So this is Edgar Allan Poe, and he said, "There came to my ears a low, dull, quick sound. I knew that sound well, too. It was the beating of the old man's heart." The author is saying he has just murdered a man who had an evil eye, and he was looking through the keyhole and spying on him, and he just got consumed with destroying this man's life. And he did so, and he buries the heart under the floorboards in his house. But the beating grew louder and louder. I thought the heart must burst. But for many minutes, the heartbeat was on a muffled sound. At last it ceased. The old man was dead. So here we have the electrocardiogram, the famous electrocardiogram, PQRS, wave, and sometimes U wave. And we know what happens that when the heart fails because of low oxygen or whatever electrical disturbances, we get what's called a flat line. And if you've been in a clinical situation, there's monitors on the heart. And the monitors are always monitoring. They have a range. If the heartbeat goes below a certain rate or above a certain rate, a monitor sounds. When it goes to flat line, it goes like beep, this long sounding siren, and the nurses come running. They try to resuscitate the patient. So we're going to talk about flat lines a little later as well. But when you're flatlining, are you dead? And so that's a topic for another discussion. In the ancient literature, Hebrew literature, when you stop breathing, you were dead. Now that's a very poor indication of death in modern time. Even the stopping of the heartbeat is a poor indication of being dead. Even the flat line on the electroencephalogram is a poor indication of being dead. You're going to be overdosed with penobarb or barbiturates, something like that, and then the brain goes silent. How do you make a heart speak? Here's an electrocardiogram, and again, we repeat. Here at the first time second, we have a P wave, activation of the atrium. QRS complex, that's the activation of the ventricles. And then the T wave is the repolarization of the ventricles, and a little bit of a U wave. And it repeats, P, QRS, T, so forth. What we can do is we can trigger off of the large R waves. It's a rapidly changing depolarization, a DVDT, we say, and we trigger it, and we mark the time when that happens. R wave, R, 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 like that. And so these are called RR intervals. And then you can make a sequence of these and plot them, of course. And what I'm going to do is I'm going to replace a cardiac interval with a letter of the 26 English alphabet. I'm going to replace it. There's nothing magical about 26, nothing. You could do this in Russian, you could do this in Hebrew, you could do this in Greek, whatever language you want. But we're going to consider a 26-letter alphabet, and what we're going to do is substitute a letter. You say, well, how do you know what letter to substitute? So here's what we do. Down here is, at the bottom of the same graph, I have DHOLIH. DHOLIH. And then we substitute in a space according to the distribution of English words lengthwise. How many words are one letter, 2, 3, 4, 5, like that. And that's just substituted in. But what happens is for a very long time sequence, we get this language. You say, what is that? Is that really a language? And I want to demonstrate to you that indeed it is. So let's take a step back. Let's go to our friend Calvin and Hobbes. Love this cartoon. Calvin's taking an an essay examination, and he's asked on this test, explain Newton's first law of motion in your own words. Now, Calvin here gets a bright idea. He writes in his own words this text. Jakob, Fub, Mug, Grub, so forth, down here. And then he says, I love loopholes. He says, you said to write in my own words, these are my own words. Are they meaningful? So here, let's hear what this sounds like.
Jak foot mag grug pub
quipsink watum gazer chumble spuzz.
Okay, you're the teacher. You're evaluating this exam. Does he pass? He passes in the sense that he used it in his own words, but I think I would call him in again and say, I'd like you to explain it in a language that I understand. All right, I've used this in different settings. Are you familiar with this children's poem? Green Eggs and Ham. Are you familiar with the author, Dr. Seuss? Dr. Seuss, famous child author who's well known in America. But he wrote this poem called Green Eggs and Ham, and that's why the ham on this table here is green and the eggs are green. Would you eat that? You know, that's not a color that we would recognize, and we want ham to be pinkish and we want eggs to be yellow and white, not green. When we were doing recurrence analysis, it was very hard to explain what this meant to uninitiated people. So I remember getting the idea. I called my wife, who was at the junior high school, and I said, do you have that book, Green Eggs and Ham, on the shelf? And she did, and so we got the book, and I worked through it, and I started numbering all the words in the text. Actually, what I did is I entered all the text into a computer program and then substituted an integer for each different word. Okay, so the first word I found was number 1. The second word was number 2. The third word was number 3. If the fourth word was the same as the first word, it would be a number 1 again. Okay, you do this. And you ask children, okay, this poem has 812 words. But there's only 50 different words. How in the world can you write such a long poem and you only have 50 words to choose from? And the answer is you reuse words. If you reuse a word, that's called a recurrence. Make sense? Is it periodic? Heavens no. The words don't, the don't come in even intervals. The words come in all different kinds of organizational patterns. So the point is that recurrence analysis says if you see an event, do you see it again? If you see a word, have you seen it before? And if you do, mark it on a graph. That's all it is. And so what we're going to do is I'll show you some graphs of this, and let's do it this way. How probable would it be to reassemble this poem from a pile of its 2,438 scrambled letters? Okay, do you ever have a Scrabble game and then somebody knocks it over, reassemble it? Well, now you got to remember who played what where. It's not so easy. So if you have a language in a book, it has 2,438 letters, forming 812 different words, and there's only 50 different words, and you drop it on the floor, put the book together, put it back together. See, it's not so easy to reassemble things. So one control that we can say is that if we have a language in our heart, as it were, and if we would scramble up the text of the heart, and we show that it quantitatively shifts, that we have destroyed a natural language of that organ or whatever you're looking at. In other words, the sequence of events that happened in the original time series were significant. So Recurrence analysis is not just dependent upon recurrence, it's dependent upon the order in which events happen. Anybody know Morse code? Go dash, dot, dot, dash, dash, dot, dash, dash, dot, dash, dash. And people who are trained, especially military, they hear this and they can really understand what's going on very fast. Now you can analyze the text from Morse code. You could say, 40% of this message is dot and 60% is dash. You with me? 40% is dot, 60% is dash. Mix them all up. Dash, 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 dot, 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 dot. What's the percentage of dots? Still the same. What's the percentage of dash? Still the same. What happened to the message? It's gone because you've lost the sequence. That's the point. So recurrence analysis takes you a step beyond standard deviation, mean, these kind of things, which doesn't care about order, doesn't care. But recurrence analysis does care, and then we can use the scrambling method to see how much it cares. So here's an example, green eggs and ham. This is Dr. Seuss, 1960. 60 years ago, 61 years ago. Here's the way the poem goes. I am Sam. I am Sam. Sam I am. That Sam I am. That Sam I am. I do not like that Sam I am. Do you like green eggs and ham? I do not like them, Sam I am. I do not like green eggs and ham, and so forth. Now, you can see there's a lot of repeats here. Sam, 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 all through here. Green, green, eggs, eggs, ham, ham. And by the way, Sam has this component am, which will line up with am here, right? So in other words, these sequences would be recurring. And you can encode this. For example, let's call A1. We'll take a look just at this segment here. And that at the bottom, integer coding, encoding, we'll say A is 1, B is 2, C is 3, D is 4, E is 5, so forth. Z is 6, 26. And you do this and you substitute. So you say, well, I is 9, A is 1, M is 13, S is 19, A is back to 1 again, and M is 13 again. You see what we're doing? In other words, we just converted a text into an integer series. And we plot it. Here is, I am, on the bottom line here, I am Sam. I am Sam, I am Sam. And it's repeated on both axes. You'll note that this blue diagonal line, every letter lines up. I lines up, so we color it blue. A lines up, it's colored blue. And it gives you this diagonal. For any time series that you do, you'll always get this because everybody looks like himself. He recurs with himself or itself. But here are off diagonal ones. This one, AM, here's AM. And then here's another one. See AM, another one, AM up here. But you can see that there's several AMs through the text. And then here's another one here, AM here, AM here. And we get this type of structure. And what's important in the recurrence analysis is if you have two or more in a diagonal line structure, that means that this line and this line, there's a recurring pattern going on. It doesn't have to be the exact same words. But what happens is that this sequence, in this case AM, is seen more than once. And look at this string, 1, 2, 3, 4, 5, 6 of them, and then 2 up here and so forth. You can count these. You can count that there are 14 points that have these dots in them. And actually, all red points have dots, so there's 14 points. And this would be a very high percent determinism. In other words, we say of the percent of the white space, 14 out of those, the number here would give you what's called the percent density of the plot, and of those, all of them are recurrent. It's 100% recurrence. But look what happens. If you scramble it, we call this normal eggs, and scrambled eggs, okay? Scrambled eggs. And what happens is the same letters are present, but their order, we've tipped the game on the floor, we have this pile of letters, we try to put them back, and we don't do a very good job. But we use all the letters are there, and look what happens is the number of dotted red boxes is far fewer than we had before. So this would mean that these sequences were critically important. So again, do you like green eggs and ham? I do not like them. Sam, I am. Here we have 44 total letters, and there's 16 different letters, and they're encoded as you see there. So here's the English encoding. Do you, and the yellow simply means where we're flipping from one recurrence to another. Do you like green eggs and ham, and so forth. And just understand there's 44 total letters in just that phrase, and there's 16 different letters. Now, we plot this. Here's the recurrence plot, normal order. And here I've shown, here's an EG pattern that repeats. This is a longer sequence, 44 long instead of that shorter one. Here's two together, here's four together, that's like, here's SA, AM, and so forth. And what all of a sudden, what this means is that when you're stringing these letters together, you are detecting words, okay? Because words are made up of strings of letters. That's all we're saying. And it can actually cross words, by the way, across the space. The spaces are taken out of here. But you can see all of these places, I've circled them, where there's at least two diagonals together. Now, the red triangle means this triangle, which is right here in the upper left. The triangle in the lower right is identical because it's a mirror image. If I'm close to you, or if I'm like you, you're like me. So that it works both ways. And so we can say, okay, there are 56 or 53 pixels which are lit up in this whole map. And of the area, which is 946, that would mean we have 5.603% of this pattern. The recurrence rate is 5.603%. Of all those 946 points, the determinism, there's 32 points, 32% of them are in diagonal line structures. So we can use that as a measure of deterministic behavior. When we scramble it, look what happens. The recurrence rate stays the exact same. It's like statistics. The mean is the same, standard deviation is the same, but you've destroyed the structuring, the diagonal structuring, and it drops down to 16%. So that's the important part. Now here's the whole 400 letters in the first 400 letters in the recurrence plot in green eggs and ham. There's 400 letters, the first 400, encoding A is 1, B is 2, C is 3, like that. And now the density of this plot is 7.4% recurrence rate. Determinism, in other words, 42% of the points are lined up in diagonal line structures. And then we have another measure, entropy. I won't go into the detail. It's a measure of complexity. We say it's 2.277 bits per bin. How many words are 2 units long? 375. How many words are 3 units long? 3 letters long? 102. How many are 4 long? 34, and so forth. And we have 578 total words when you add all those up. Let's scramble it. Here's the scrambled. Recurrence rate stays exact same. Determinism drops. Before it was 42%. Now it's down to 15%. Entropy, 2.277, but its complexity drops down to 0.47. How many words are 2 units long? Well, it used to be 375, now it's 403. How many words are 3 units long? 102 drops to 37. How many are 4 units long? 34. Before, now it's 3. And all the rest are zeros. We've chopped up the text, mixed it all up, and we have fewer words. Now, Here is the embedding of all 2,438 letters in green eggs and ham. I've added one thing, and that is embedding. Embedding means take not just one character and match it with another character looking for its same self. Take two characters at a time and see if you can find that two character pattern. Take three letters at a time and match it. And so I've done this from 1 all the way up to word length 20. Okay? So that means I have to have a string of 20, and that exact sequence has to match the same sequence of 20 later on in the poem. Okay, that big word. And what happens is, when you increase the embedding dimension like that, the recurrence rate drops from 10, it's dropping fast, 1, this is a log scale, then it goes down, 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 almost to 0.1. So that goes down. But after you shuffle the data, look what happens. It goes down rapidly. In other words, there's no word longer than 4. No word longer than 4, so embedding doesn't do anything. So this would be after it's been scrambled. So the green will always be the scrambled version, and the red will always be the non-scrambled version. And here's what happens to the determinism. So the determinism goes up, and look, it really kind of saturates, and that's when you have this large embedding dimension. And then the determinism falls rapidly, there's no word longer than 4. And so this difference between deterministic structure before the red, after the green, says that we're dealing with real words. We're dealing with words. And here's the entropy. It goes up, stays pretty high, and then the entropy, it's low to start with and drops off after you shuffle. All right. Here is a sequence of RR intervals from the heart. First, in other words, this would be the duration between heartbeats. The closer the beats are, the shorter the time interval. And the longer time interval between them, the longer the interval gets longer and the heart rate goes down. So heart rate is very fast at the lower level and very slow at the top. So in this case, we have a mean. The average RR interval is 0.92 seconds, and this is the sequence. You scramble it, and it looks like this. It does nothing to the mean or the standard deviation because it's not sensitive to sequence. Now we'll see what happens here. If you would distribute the RR intervals into a histogram, here's what it would look like. That's what it would look like. So you have tails on both sides here, and we have averages. You could study that by standard deviation and mean and so forth. Wouldn't mean a whole lot. But there's 400 RR intervals here. What we do, see this big bin right here? We rank order the bins. We rank order them. So we say, well, this is the biggest one right here, this pink one, and we're going to put it up here. We're going to put it in the first position because that has the highest count. And as you go down, it goes down, 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 down. And what we do, if you look at maps which are published, what's the most common letter in the English alphabet? E. What's the second most common letter? T. What's the third? A. So if you look at these word games, there's TV shows where you guess a letter in the pattern, and you know what letters to pick first. You want to pick in consonants. You want to pick a T, you want to pick an N, an S, and R. Those are the ones that you pick because those are the most common ones. You don't start out and say, well, I'd like to see a Q, because Qs are not very common, okay? I think in Polish, Zs are real common. Real common. Actually, I used to play, we were in Germany for a couple of years, and we played Scrabble with Germans. And I said, boy, does this Scrabble game have a lot of Zs in it? It really does. I didn't get there yet. So what I'm saying is that this would be the this RR interval is most common, whatever this is in terms of its bin, okay? And they're just numbered according to 26 letters, or 26 numbers, okay? And then we take the first, the largest one, and we just rank order the bins. Then we back map like this. This is your answer, Joanna. So what we see is that on this scale, here's the absolute RR interval in seconds, okay? And this is beat 1, 2, 3, 4, 5. So this is cardiac cycle number. There's 400 of them. And then here's the mapping of them to the letter, like we showed in the previous slide. So here's E, most common. So E, if the counts in this framework right here, that's the most of them present, and that becomes an E. But you can see that they're all jumbled up because of the sequence of the RR intervals. But we can come up with a text. This is the largest one, the maximum, the minimum, and so forth. But look what happens now. Here's the normal heart speaking. I'm mapping it back to a text. So that we're saying here, you want to hear what it says? Here's what it says.
Hasselgwisiat
Dre speaks. Normal heart speaks. Stasamel CTAIUCO evac gugli RA amusiel gliens mutasselgwisiat Dre CILMMEI had is thico CIID tot tesitat ir hostesia osclara ICLC EL CAPNKV huafk.
It sounds like Latin. The spacing of letters is according to the distribution of length of English words. So in other words, an average English word may be 4 or 5 units long. Two-letter words are very common. 7-letter words are less common. 10-letter words are very infrequent. And so we just pop in to the distribution. We interrupt it with a statistic which maps or matches the distribution of word lengths. It has a lot of letters. Yeah, because that's part of the distribution of letters that came out randomly. It's a random. So here's the recurrence plot of that. And these are normal order. So the recurrence is 7.3%, determinism 23%, entropy 0.7. And we have words 2, 3, and 4 letters long. That's it. Here's your ubiquitous line of identity. Now, is this meaningful? Well, the text is not meaningful in the sense of understanding, but is it meaningful in the sense of the length of words that we find in sequence? And so we scramble it.
Scrambled heart speaks.
Scrambled heart speaks. Lir edgerel morsel urelio KIHVIEC AHCT NACITZ clear white OIOE ATESE tat ton runicahid to so re EUUII badnir mu IAAFA goat de lave smicersi to lidnitten re act gald rowie.
Now, if you could distinguish those two texts, you're pretty smart. We need to collaborate. And here is the plot. A lot of people like recurrence plots because they're beautiful. One fellow, I helped him with the program, and he called them spiritual plots. Another friend embedded in 300 dimension of 300, and I said, "You can't do that." And he says, but it makes pretty pictures. And it's true. If you take a random time series and embed it 300 times, you will get nice, smooth, multicolor, psychedelic pictures. And it attracted him. Okay, so when we did this scrambling, the recurrence rate stays the same. It has to stay the same, but determinism went from 23%, fell to 15%. Entropy, it's less complex. Scrambled eggs are less complex than non-scrambled eggs. Words, there was 531 words that were 2 units long, it dropped to 405. There were 3-letter words that dropped from 89 words to 28, and that's it. 4-letter words, there were none. There were no more the more you embedded, and we only have 433 words. So in other words, what we're saying is that they're different. They're they're different. Now, this is group statistics for 34 different subjects. And what we're plotting is recurrence or determinism. Recurrence is on, let's see. The recurrence is black and the determinism is red or green. So the recurrence, and here this is the subject. So this subject number 1 had recurrence of about 17%, and I've rank ordered these as well. So the lowest one comes way down to here. But these are 34 different subjects in black. Then subject number 1, we have what's the recurrence rate in the normal ordering of cardiac cycles? Okay, what's the normal ordering after they're scrambled? What happens to determinism after you scramble it and it goes drops? You see that? There's a big drop for subject 1. Subject 2, big drop. Subject 3, big drop. Subject 4, not as big a drop. These are rank ordered according to recurrence rates. I've picked out, and by the Wilcoxon non-parametric test, the p-value is less than 0.001 in this whole cohort of 34 patients, meaning that when you scramble the recurrence intervals, you've lost structure. It's less complex. You've destroyed the language, okay? If I pick 3 here out of this file, this one has a huge drop. This one has a moderate drop after scrambling, and this one hardly has any drop. In other words, there's a variety of things here. So here's the first one, big drop. Here is the RR interval time series from which the red values are computed. And then we're doing this over, we're increasing the embedding from 1 to 8, for example. So here's the native order is red, and then after you scramble it, it goes down faster. What that says is that the order of these intervals are very, very important. The determinism, again, as the embedding goes up, the scrambling has a big effect. So just look at the red versus the green. So here the green and entropy, less complex. These are 3 measures of 8 standard ones that we use. Here's one that didn't have as much of a change. So you can see that it's not quite the same. And you can compare the time series if you want, but the numbers the data are seen in the numbers, not so much the pattern of the RR intervals on the bottom. So here we can see the red versus the green, entropy. There is no entropy here in that last bin after you scramble because we don't have that higher structure. And then here's the one hardly any change at all, even with embedding. And so look, slight down. Even this one goes up at this embedding 3 for this subject. But you put them all together, and what we're trying to show is that the language has been disrupted. It's a little more complicated to explain, but the point is that just look at the recurrence plot. This is a recurrence plot. Those trained in this would realize this is an embedding of 1 because you get a crosshatch pattern. It looks like a checkerboard on its side. And that's what a sine wave would give you. And because this sine wave I've converted it into only 26 bins, the sine wave, when you get up to the top of sine wave, it very slowly changes, but they're all falling in the same bin, okay? That's why it flat tops it. And that's why we get the square in the middle. When you do what's called frequency encoding, instead of going by the 26 bins like that, you get, the pattern looks very, very different, but you get the identical pattern here. So embedding is 1, radius is 2. In other words, we're looking for exact matches, and we insist on the shortest word being 2 units long. So these are the same. Recurrence rate are identical, 5.8%. Deterministic rate, 79%. Entropy, 2.7. This is just to show you that when you're mapping properly, it doesn't matter what map you use. They'll come up with the exact same information. And if you're familiar with Hénon character, do you teach Hénon attractors and things like that? So this is a strange attractor Hénon system. You don't need to worry about the mathematics, and it's an iterative system. It has a nice shape and phase space. It's fractal. In other words, the deeper you look, it keeps emerging. The parts keep emerging. And anyway, I've encoded it according to the alphabet, according to a 10-letter alphabet or a 100-letter alphabet. If you have a 10-letter alphabet, you get the graph on the left. What that means is subtle changes in the signal all fall in the same bin, right? If you have a 100-letter alphabet, now you have fine discrimination. So it's like fine tuning. And when you do that, now your recurrence plot gets less dense. But nonetheless, you have these streaks, these lines. It looks like taking a shot, hold a camera to the sky and do a time exposure, and you see the star tracks. The same thing. But they're very faint, but here it's dense. So it's just a different encoding. And you can say it's a different language. And here you can see the numbers here. When you have a very small alphabet, you get high density plots. The determinism, though, it's not that much different in this case. And the entropies are pretty close as well. But it's that recurrence rate which is being affected here. So you say, well, what do I pick for the alphabet? And the point is this, is that you don't worry about what language, you don't worry about 26, you don't worry about 10, you don't worry about 100. You can let your system set its own alphabet according to the resolution that you want to work at. And then you can tune it by your recurrence, the radius threshold, and you can say who you're going to accept and who you're not going to accept. And those are some of the details that you can study in recurrence analysis. But my point is that the system you're dealing with is a language. That's all I want to make. That's the only thing I want to say. It's a language. It's a language. Things are speaking at you. This is close to the end here. Now watch this. This is what we call, here's a cardiac disease of atrial flutter. In atrial flutter, the heart rate is going 150 beats a minute. Now you can get your heart rate up to 150 beats a minute if you do some strenuous exercise, and that's okay. That's about the peak of cardiac output. As you increase your exercise and your heart rate goes up to 150, you keep increasing cardiac output. If you go above that, though, you're contracting so fast that you don't give time for the ventricle to fill, and your cardiac output actually falls off when you're going at 160, 170 beats a minute. So it's not productive. But when you're in atrial fibrillation, that's the precursor for an atrial fibrillation, where it goes totally out of control. So here's the text. We've converted it. Guess what? Here's the RR interval. Here's the RR intervals. Since this is so regular, it's very periodic, very, very periodic. So that would be high determinant. Look, look at this. What's the most common interval here? Well, this one is. What's the most common letter in the English alphabet? E. So that's why we have this. So here's what it sounds like.
Pathological heart speaks.
Pathological heart speaks. TDL HIOCAR.
He's dead. Maybe we could substitute this for a more interesting alarm system. Let me bring it back to literature. This is New Testament literature. Romans 1:20. For since the creation of the world, his, God's, invisible attributes, his eternal power and divine nature have been clearly seen, being understood through what has been made, so that they are without excuse. The point is that nature's speaking. Nature is speaking. And we need ears to hear and eyes to see. Here's another one. Jesus answered, I tell you, if these these become silent, these people, the stones will cry out. How does a stone cry out? You can actually take a stone which is striated. You can encode that into letters. You can do a recurrence plot, scramble it up, show that you're messing up its language. Rocks speak. Okay? Rocks speak. And Job 12:7. Here's the charge to biologists. Now, Job, go ask the beasts. Let them teach you. Go ask the birds of the heavens. Let them tell you. You say, well, what do beasts say? What do birds say? They say a lot. They really say a lot. And this is my last slide. Well, no, not last, just about. Here's the conclusion. Signals detected in time and space constitute information, but is that information meaningful or nonsensical? Recurring patterns within such signals can be deemed informative if signal scrambling destroys the patterns. That's the scrambling part. And patterns of signals within any discipline can be viewed as structured languages, albeit non-readable. Can't read it. But the information is in there and in your numbers and how to interpret that. It's concluded that the natural world at all levels is speaking to us. What's the message? What's the message? So you can see we can cross all disciplines here, from literature to biology, psychology. We could talk about EEG patterns, right? We could do that. We could talk about someone used recurrence analysis a long time ago. He encoded words from patients with stroke and claims that you could tell a stroke patient by the sequence of words that were selected. And recurrence analysis would pick that up. So thank you very much. This is a website if you want to get some software. This is inspiration for my favorite composer is Chopin, and was at a concert this past week, hearing him. And you know why I like him? Because I was encoding music, and I soon came to realize that the beat count doesn't add up. It does not. Quarter notes, eighth notes, 16th notes, and I say, wait a minute, this measure should have this number of counts, and it doesn't. And so I asked him, I said, what is this? So it's like a Picasso of music, you know, Picasso. So what I'm saying is that okay, but you could still, right? So the point is, when writers get writer's block, maybe musicians get composing block. So you look outside, you see the birds on the wire, and you have a melody pointed out right here. That could be played on a piano, the way birds sit on the wire. Thank you very much.
Thank you so much, Charles. And yes, and I wanted to thank also TrainCrease, which is a grant that made possible the visit of Chuck, and also his tutoring on our future recurrence plot workshops that we are going to hold here at Warsaw University. So we will take some questions now and stay here for another 10-12 minutes, and then we will have another room for data session when we can open our computers and do it there. So are there any questions here, or please do also ask questions on YouTube if you're there. I know that at least some people are there, so I wave to them. And if I may, just with a short question that is nagging me since the conference in Lublin. You said right now also in this lecture as well that entropy of diagonal lines is somehow a sign of complexity. And also I saw at the conference that people are equalizing determinism with complexity or lack of it. Could you elaborate on what
Yeah.
complexity actually means here?
There's 2 points to look at. Sine waves give you diagonal line structures, and what my lecture in Lubun was about is that when you truncate the borders, it makes all the line lengths different lengths and actually maximizes entropy. We're viewing entropy from the standpoint of information theory, so it's a P log P calculation, and what we're saying is that for a sine wave it would be very low, it'd be zero entropy actually because it's totally repeating, and so that's why we put the correction into the software. So yeah, the information complexity can be measured by the distribution of line lengths being different. So if the line lengths are, in other words, in the terms of the recurrence plot, like the Dr. Seuss, some words were 2 letters long, 3, 4, 5, and it was quite a mix of those. And that would mean it would be a high entropy. So if it was a poem made up of just 2-letter words, then, and if every word was just 2 letters, the entropy would be 0 because you're looking at probabilities. The probability, in other words, you have 5 2-letter words in a row. What's your guess on the next one? Well, I'll guess 2. Because it's very, very predictable. But in other words, the longer the words and you're dealing with sequence, it gets harder and harder and harder to predict the next word. So that would be the statistical distribution of that.
Yes, but as we all know, complexity measures can be different. And cognitive science is sort of grappling with this problem of what is a complex organism. And, you know, we are so surprised that zucchini has a bigger genome than we do. And that's sort of, we think it's unfair because we think we are much more complex. So this is maybe not the best way to describe complexity. By the length of the genome or of the computer program like Kolmogorov complexity. But it seems that the length of diagonal lines, for example, the entropy of this, which is different than the entropy of the signal itself, can tell you something more. Is there a hope there? Do you see it as?
Yeah, maybe we should talk about filters. Principal component analysis is a grand filter. It'll take, you can have 10,000 inputs, and you boil it down to 3 variables. This is a big filter, right? And so what are the 3 most important variables in this system? And you say, well, what about all the other hundreds? And what that means is that they're lined up. In other words, if you're studying arm motion, you can do it by the muscle tension, you can do it by the angle at the elbow, you can do it by the position in space. There's many ways to say the same thing. So those variables would all collapse into one. So is that complex or not? Well, I'm glad I have a wrist and an elbow and muscles. So I want that kind of complexity. Yeah, they're working together. So people who are talking together, this is your field. So if you got 2 people and sway, so if you sway, like if you invade a person's personal space, I know people who are real nervous, you get into their space and you can literally see them back up, literally. And other people, they'll come right up to me real close and I don't back away. And then it's like, but it's a little uncomfortable. So I mean, that's a psychological thing, but the complexity depends on your question. And
yeah, this is another thing that I really liked about the recurrence analysis, that really you have to think hard about your phase space, which is determined by a research question, right? And this is something that we think maybe we should think about complexity modulo some research question, or yeah, in reference to research questions and not to organisms per se. I don't know. Okay, any other questions?
Right. So Hi. Thank you for the talk. First, a silly question, because I'm not sure if I get it properly. So from your talk, I got that the recurrence analysis is basically it's a comparative analysis. So you always compare to the sort of base state of randomness. So you basically say you take some data, you try to make it into some kind of discrete system if it's not obviously discrete, and then you compare the state with the analysis or the entire data as it is now, and then you scramble it in some according to some rule and basically see the difference. Is that it?
Mhm.
So it's a sort of a clever test for saying how much structure there is in data without saying you don't. Well, it says something about what kind of structure it is, but it's mainly a measure of structure in general.
Right.
Right.
Right, and it's one thing to say, okay, there's structure here, and you can measure it in terms of entropy and all. That's okay. What's more important are transitions between phases. That's the key. So in other words, you have this state, and then you go to this state. This technique allows you to determine when you're in a transition. Okay, you're changing states. So for example, the recurrence analysis, you could view it as it's like a mathematical microscope or telescope. It's like a microscope. If there's nothing there, recurrence can't find it. But there might be something in your signal that you can't detect in your linear tools that the nonlinear tools will detect. So if you know anything about from earthquakes, volcanoes, storms, farmers, if you want to see if a storm's coming, you don't look at the sky, you look at your chickens. Because the chickens detect a change in the electrostatic electricity in the environment, and their behavior changes, so you observe their behavior. And so what recurrence analysis is it's a better chicken.
Yeah, I like it. I like it, especially the chicken comparison, because it seems that, which is interesting for the stuff I'm doing, is that it also serves as a sort of a tool to detect events. Like you collapse all of these different variables into just a couple of them, and you put them on a plot. And if the main thing that you can detect is transitions between phases, you basically mean these are different events. And then you can sort of, let's say, have a fractal recurrence analysis when you do the same on those events. And then you try to study them according to the similar rules. That's interesting. So do you do this sort of is this what embedding is really about? Like you have one structure and then you try to
well, embedding is trying to capture in a single number the number of states or variables operating in your system. So if you under embed, so if you have a complex system with 10 dimension and you embed in 5 dimension, you're missing pieces of the whole puzzle. So in other words, you're trying to capture in a larger embedding space. In other words, if you want to study a 3-dimensional object, in 1 dimension it's 0 dimension, it's just a point. In 1 dimension it's a line. 2 dimension it's a flat surface. 3 dimension gives you the cube. But why stop there? Let's go to 4. Let's go to 5. Let's go to 6. You say, I can't draw that. Yeah, but stop drawing. Just understand what embedding means. You don't need to draw it.
They're pretty. So. Right.
Yeah, the thing about phase transition is, and the better chicken idea is, can you use the analysis as a better canary in the mine? You know, is there carbon monoxide there? Okay, we can't smell, but the bird can, and so when the bird keels over, you say, time to get out. So in other words, the transition between phases can be important. I'll give you an example. There was a Japanese researcher using recurrence analysis on iron smelting. Iron, ferrous. And it's a very complex reaction going from iron 2 to iron plus 3 states, and all these different iron oxide mixes. And what happens is that you have to have an even heating of the thermos of the smelter to produce a pure iron that you want without the oxygen. And so what happens is that he put sensors on the different heating elements. And the point is that when a heating element would fail, you would get a change in temperature, which would affect the product quality. And he claimed that he could use recurrence analysis to detect when there was a failure of the unit, which would then, in industry it's important, which would then say, hey, wait, you better shut the whole thing down because the quality of your product is poor. So that becomes a practical observation or use of this. But in other words, again, we're not here to study cadavers. We're here to study state changes and things that wiggle in time and space, and when does it change? And that recurrence is really good at that, really good.
Right.
Yes?
Flat line, yes, of recurrence, and then it's changed rapidly into some gibberish.
Yeah.
Right? So you can see.
So that's what I mean. In from normal to pathological, there's a speech shift, which would just, in recurrence terms, well, the recurrence rate changes, the determinism changes, the entropy change, well, things change. And so you look for those changes.
I think the Boris' question was very pertinent also to us psychologists, because when we talk about physical variables and the work of engineers or physicists, we had great examples from ball bearings, for example, how they work and how to detect their malfunctioning, etc. But it's kind of easy to describe what a state is, or what is a recurrence, the recurrence of what. And what Boris was getting at is that people, we have this discussion in psychology, what is a stimulus? And how does it recur to us? And in psychology, it's treated as so obvious that a stimulus is something simple that is repeatedly coming to us, which is not exactly true in a world that is dynamical, and it's difficult to chop it into stimuli. And what Boris was asking, I think, was can you use the recurrence analysis even to detect those what recurs, or you have to assume what recurs and then use the recurrence analysis as we do. So is it so that we could even see how to chop the reality? Is it a good question?
Again, it depends on the question, and it depends on the perspective that you take on it. I mean, even in there's artwork, you look at it, and we just saw it in the museum yesterday. You have these straws, and you look a certain way, and it makes a chair. But from another perspective, it's just free floating. Doesn't make sense. So it's an interesting question. What would the stars look like if we could go 100 million light years from here? And it would be very different. You would not. The constellations are made up of stars that are very far. They're not right next to each other. It's the perspective that gives you the pattern. So it's the same thing. Let me say this: psychology, sociology, philosophy, religion are called soft sciences. Physics, chemistry, mathematics are called hard sciences. Now listen carefully. If you're dealing with mathematics and your system can be described exquisitely with mathematics, you're dealing with simple systems. If you cannot describe your system with mathematical equations, differential equations, all this stuff, and the best you have are statistics, you're dealing with a hard science. That's why physicists don't believe in standard deviations. You do the experiment once, you don't need any more, because it's always the same. Boring. You know, so the point is, and people are different. So that how many people my knowledge is, I think people in psychology and sociology are better statisticians than people in other sciences. We're happy with 10 and the p-value is 0.001 and this is good. And you would say you're dreaming, right? We need hundreds, you know, so we talk about COVID data and all these types of things. A population of 10 or even 40 people in a study is nothing.
Maybe on your comment, maybe recurrent analysis can help you to detect what is the proper length of signal that you want to observe, because like with language, you have letters and you have words. So depending on the embedding, yes, how long you look in the past, you can see that either it's a string of letters or it's a string of words which give you more meaning. So you can see there are some emergent states if you look longer sequences. I'm not sure if I understand it well, but can recurrence analysis help with that to show you that there are some more, you know, some emergent states that are above like the single event you observe. Right?
Yeah, I didn't introduce it, but the concept of windowing. So in other words, you have this long data series. No, that's different. It's, yeah. Right. And windowing is how long is the whole series that you want to submit to recurrence analysis. So you say, I want to submit all my data, 500 million points, and you get a recurrence plot. Now, there's no computer that does this, but what would it would average everything. Everything would be sort of averaged. And then you say, well, let's look at microstates. And you can. And you can say, well, let's view this part. And a lot of the microstates are right along that line of identity. But you can move your microscope up and you can look in this corner and this corner, and people are recognizing there's different by looking at the visualization. I've downplayed the visualization, but there is something to say about seeing patterns in the visualization that is more intuitive than even the recurrence variables that we compute. You use the variables for your statistics, but your eye, you say there's something here. And then you can focus in on that. So you actually, there is some usefulness in looking at the actual plot itself. Yeah. So it all depends on your research question. The hard part about recurrence analysis is how do you set all the parameters, 5, 7 different parameters. That's the hardest thing, especially setting the radius.
There is also a question from YouTube, and but it's a question that probably was similar to Boris's question. Do I correctly understand that the purpose of scrambling the data is to provide a random baseline for the measures calculated on the actual unscrambled data? And you answered that yes.
The answer is yes, and it's a.
But to just follow this question, but can we also use compare the structure taking different units, recurring units into analysis? So yes, we can, right? Yes. Like letters and words.
Right. So often what we do when you're looking for transitions between phases, we don't worry so much about scrambling the data. We just say if the determinism's high, it's already structured, so we know that. But we say, okay, the deterministic structure is going down. We're in a phase transition. And that, in other words, the baseline of the data itself becomes the reference point, not a scrambled version.
Right.
So I rarely scramble. Rarely.
Okay.
This is just for illustration to explain.
Okay, and if you have recurrence analysis on different units of data, let's say, do you always see transitions at the same point, or?
Depends on your system. Depends on your system. Depends on your perspective. You know, if you're looking, if you have a sine wave seen from the side, you'll see it wiggling like this. But I'm going like this right at you, or with a pen going like, is it moving? Is it not looking to move? You got to change your position to see it. So again, it's dependent on perspective.
Thank you very much. Any more questions? If we don't have questions here, then we can stop the recording. Thank you very much, and thank you for coming. And thank the train crews again, which I forgot to do at the beginning. And